Hello students, very good afternoon to all of you. Today I will explain to you method of the strain energy, how to calculate the deflections, vertical deflection, horizontal deflections, Castigliano theorems, Maxwell theorems, Betti's theorem. So this is also one of the important chapter of the structural analysis. So let's start. Strain energy. What is strain energy? As I explained in my earlier lecture, strain energy is that energy when an elastic material is deformed under the load, work is done by the applied load against the internal resisting forces induced in the material. The work done by the material by the load in straining the body is stored within the strained material in the form of strain energy. Since strain energy is of the body is defined as the work done by the load in straining it, it is always a positive quantity and is expressed in work unit, that is Newton meter or joule. So suppose this is a bar and I have applied a force. So resistance, if I cut it, then it will be like this. So resistance will be developed internally, and as a result of resistance, stresses will be developed, internal resistive forces will be developed, and as a result of that, work will be done, or we can say the energy will be absorbed in the form of strain energy, and this strain energy is equal to the work done. Work done is equal to force into distance. So work done is equal to the strain energy. This is my load deflection diagram, as I explained in my earlier lecture also. Suppose this is a bar and I have applied a tensile force. So there will be some elongations delta in the direction of the applied load. If I draw a load deflection diagram, then it will be like this. This is my this one is the x-axis, this one is y-axis. The deformation is plotted on the x-axis and load is on the y-axis. So my load deflection diagram, as my load is increased, deflection will also increase. So it will follow this kind of path. So this will be initially it will be a straight line, and thereafter it will follow a parabolic path. So and finally this is the ultimate load and this is the final deformation delta. So as I increase the load gradually, my deflection will also increase gradually. Suppose at when the load is P1, then my deflection is delta 1, and if I increase my deformation by delta 1 due to the increase of the load, that is delta P1. So work done for this portion will be equal to the load P1 into P1 is that this ordinate is P1 into delta 1. Suppose consider this as a small strip, as a rectangle, so it will be P1 into delta 1. So if I integrate it from 0 to delta, then what I will get? I will get the total work done. Total work done, or I can say strain energy. So this P1 into delta 1, if I integrate from 0 to delta, I will get, and this P1 into delta 1 integration from 0 to L is nothing but the area of this hashed portion. Area of this hashed portion. So area of this hashed portion will give you the work done, or you can say the strain energy stored. So when the load is applied, resistance is set up in the bar, and this is stored in the form of strain energy. As the load is increased gradually, this resistance is increased gradually. For evaluating the strain energy, we plot the load deflection diagram, that is resistance deformation diagram as shown. The work done during the incremental deformation is P1 into delta, represented by the hashed. So total work done is the integration. The work done is equal to the shaded area of the load deflection diagram. Shaded area of this one. This is the load deflection diagram, shaded area. The increase in load P results in an increase in the strain, which results in an increase in the energy level of the bar in the form of strain energy, which is defined as the energy absorbed by the bar during the loading process. The strain energy is equal to the work done by the load. So strain energy U is equal to W. If I integrate it from 0 to delta, I will get this one. So when the load is within the elastic limit, when the load is within the elastic limit, then my diagram will be like this. So initially up to the proportional limit, the diagram is this line is straight line, and thereafter it will follow a parabolic path. So if I consider my work done up to this, then it will be nothing but a right angle triangle. Suppose at this point my load is P and deformation is delta, then area of this triangle will give you the work done, or you can say strain energy. So the load, this load is P here and this is delta. So area of this half of P into delta. So this is the work done, or you can say strain energy, and 1 upon 2 P into delta. And what is this delta? Delta is the deformation. And what is the formula of deformation? This is PL upon AE. So this is a change in length. This delta is a change in length. So change in length upon original length is equal to strain, and strain is equal to stress upon E, and stress is load upon area. So this change in length delta will be equal to original length into P upon A into OE. So as I increase this explained in my some lectures, so delta is equal to PL upon AE, as we know. So it will be P square L upon 2AE. So this is the formula for the strain energy stored in case of axial bending. In case of axial bending, like this. This is a case of axial bending. My strain energy stored will be P square. This is L upon 2AE. A is the area of cross sections and E is the modulus of elasticity. So U is equal to P square L upon 2AE. This is work done, or you can say strain energy. This is equal to P square L upon 2AE. So whenever there is a axial bending, so this is the formula. Now as we know, strain energy is equal to W is equal to work done, and this is equal to load into displacement by 2. and this P is equal to, this P is load is equal to resistance, and this is equal to stress into area, as stress is equal to load upon area. So this P will be stress into P A. So stress into PA, and this if I divide it by L and multiplied by L, so I will get this one. Now 1 by 2, this is P, and A, and A into L I will take here, A into L, and this is change in length upon original length. Change in length upon original length is strain. So this is strain E is equal to change in length upon original length. So it is 1 by 2 stress into strain into, and what is this? This is the area of the cross section A into length. A into length, what we will get? We will get volume. It means 1 by 2 into stress into strain into volume of the bar. What I will get? I will get strain energy. So this is the another way of expressing the strain energy. So strain energy we can say it is equal to 1 by 2 into stress into strain into volume. 1 by 2 into stress into strain into volume. This is the another way. Or we can say U is equal to 1 by 2. This is stress is P. Strain is equal to this one. As we know, E is equal to modulus of elasticity is equal to stress upon strain. So I can say my strain is equal to stress upon E. So this strain is equal to stress upon E into volume. So now it will be P square upon 2E into volume. So this is the also the another way of expressing the strain energy. So strain energy is equal to stress square upon 2E into volume. If I divide this U by the volume here, so it will be U upon volume. So this will be strain energy per unit of volume, and that will be equal to P square upon 2E. So strain energy per unit volume is equal to stress square upon 2E. Strain energy per unit volume is equal to P square upon 2E, and this is their resilience, or we can say strain energy density or resilience. So this is ability of the material to absorb strain energy within the elastic limits. So this strain energy per unit volume is resilience or strain energy density. This expresses the ability of the material to absorb energy within the elastic limits. When this stress P becomes proof stress at the elastic limit, if I express it F, proof stress at the elastic limit, then it will become F square upon 2E, and this is resilience, or we can say modulus of resilience. When this stress becomes my proof stress, then it will be F square upon 2E, and this is modulus of resilience. So another way to express the U is, as we know, U is equal to P square L upon 2A, and this P square L upon 2E, if I write it P into P, then it will be P by 2 into PL upon A, P by 2 into PL upon A. And what is this? PL upon A is delta. As we know, deformation is equal to PL upon A. So P by 2 into delta. P by 2 into delta. And what is the P, capital P? This is the load is equal to stress into area. As we know, P is equal to P upon A. So P is equal to P into A. So PA upon 2 into delta. And what is this P? P is equal to stress. Stress is, as we know, stress upon strain is equal to Young modulus of elasticity. So we can say this P is equal to capital E into strain E into E. If I express E into E in place of this P, it will be E into A by 2 into delta. So it will be E by 2 into this strain. And what is this strain? Strain is equal to change in length upon original length. So this will be E by 2 into change in length upon original length into area into delta. So it will be E A delta square upon 2L, or U is equal to E A delta square upon 2L. So this is the another way to express strain energy. So another formula is strain energy U is equal to E A delta square upon 2L. So this is E A delta square upon 2L, then F square upon 2E into volume, P square upon 2A is equal to into volume, this is 1. Then we can say U 1 by 2 stress is strain into volume, or we can say P square L upon 2A. So these are the various way of expressing the strain energy. Now strain energy due to bending. So there are two cases. First case is pure bending. So in case of pure bending, suppose this is a simply supported beam. This is a simply supported beam. One is roller, other is hinged. So it is subjected to a uniform bending moment. Then its bending moment diagram will be like this. So and since my bending moment is constant everywhere, so it will deflect like this. So in case of constant bending moment diagram, this will be a circular arc. If I draw a tangent, so it will be a circular arc. This is radius of curvature R, and this one is L. So L is the length. As my R is very larger than this L, so I can say this L is equal to L. So theta is equal to L upon R in this case. And what is R? Radius of curvature. So in case of pure bending, as we know, M upon I is equal to E upon R is equal to F upon Y. So 1 upon R will becomes M upon EI. M upon EI. So if I put this is L into 1 upon R, it means L into 1 upon R is equal to M upon EI. So I can say this theta is equal to ML upon EI. So theta is equal to ML upon EI. If I draw the load deflection diagram, then it will be like this. If I increase this M gradually, both sides, M1, M2, M3 equally, if this is M1, this is M1, this is M2, M2, like this. So my load moment rotation diagram will be this way. As I increase my this theta 1, theta 2, theta 3 like this, M1, M2, M3. So as I increase, so it will be moment rotation diagram will be this way. So it will be a linear, as this is a linear expressions. So as m increases, my theta will increase linearly. So it will be a straight line. This rotation is being plotted on the x-axis and m is on the y-axis. My diagram is like this. So it will be a straight line. Now finally, if this is within the elastic limits, suppose this is m and this is theta, then work done will be equal to the area of this moment rotation diagram. So area of this moment rotation diagram will be this m into this is theta, this is m. So work done is equal to area of this is m into theta. This is 1 by 2 into m theta work done. And why this work done is equal to how much? Work done is equal to strain energy stored. So I can say my strain energy or work done is equal to 1 by 2 into m theta. And what is theta? If I put the value of theta here in these equations, what I will get? I will get 1 by 2 into m, and theta is equal to ml upon ei. So it will be m square L upon 2 ei. So this is the formula for strain energy stored in case of pure bending. Pure bending means it is a circular arc. So strain energy stored formula will be m square L upon 2 ei. So in case of pure bending, this is the formula for strain energy stored is equal to m square L upon 2 ei. Now what happens when the bending moment varies? In this case, my m is constant. In case of variable bending moment, then this formula will not work. So suppose this is a simply supported beam. So if I draw the bending moment diagram, it will be like this. The maximum ordinate is, suppose this is W per unit Ren. So it will be W L square upon 8. So my bending moment diagram is parabolic. It means at a distance of x, my bending moment is mx. So the bending moment is not constant, it is varying. So in this formula, if I want to derive the strain energy formula, then what I will do? Suppose this is this one is the deflected shape. So like this simply supported beam carrying UDing. So its deflected shape will be like this. So if I consider at a distance of x from this end, if I select a very small distance of dx, and if I draw two tangents, then normal to this tangent will meet here. So this, if this is, suppose this is theta, d theta. So this d theta is equal to this dx upon r. Dx upon r. So dx upon r is d theta. So suppose at this if I consider 2 points, so this distance is from this end is dx and this is dx. So normal to this, there is only a angle d theta. This is dx, this is the radius of curvature. So this d theta is equal to this length dx upon r. And what is So it means it is 1 upon r into dx, and 1 upon r is equal to how much? M upon I. If I consider, suppose the moment here it is mx, this is mx, bending moment at this x, which is x distance from here, this is mx. If I consider some bending moment is constant, since this is a very small strip of dx, so I can say my bending moment is constant, mx is constant. Then formula of this will be, as we know, m upon I is equal to f upon I is equal to E upon r. It means 1 upon r is equal to m upon EI. So m is mx here, so it will be 1 upon r is equal to mx upon EI. If I put the value of 1 upon r is equal to mx upon EI here, so what this will be mx upon EI mx upon EI into dx. So d theta is equal to mx into dx upon EI. Now work done for this portion, suppose work done is equal to dw or d strain energy for this dx portion, both this small portion, suppose the strain energy is du. This will be equal to 1 by 2 into moment into theta by 2, as we discussed earlier. So moment rotation diagram, this is theta, this is m theta by 2. For this portion it will be mx theta by 2, mx theta by 2. This is the formula of the work done or strain energy. So 1 by 2 mx, and this theta is for this portion it is a d theta. So mx into d theta is, since I have considered this small strip, so this theta is equal to d theta, and this d theta is equal to mx upon EI into dx, mx upon EI into dx. So it will be 1 by 2 mx square dx upon 2I. So this is the strain energy stored for this portion. If I integrate it from x is equal to 0 to L, this length is L, what I will get? I will get the total strain energy stored for this beam. So total strain energy stored for this beam U is equal to integration of m square dx upon 2EI from 0 to L. This is for this dx strip, and if I integrate from x is equal to 0 to L, I will get. So this is the formula for total strain energy stored in case of a variable bending moments. This formula I can also derive from the other way. I can also derive it as below. Suppose this is a simply supported beam, this is the cross section area. So at a distance x from here, if I consider a small strip dx, then this one is the neutral axis. So at a distance of y from the neutral axis, if I consider a small cylindrical strip, having a cross section area is dA, cross section area is dA. At this level, if I draw the stress diagram, it will be like this one. So suppose this at this level, this is F. So my bending stress is F, and F m upon I is equal to F upon y is equal to E upon R. So it means F is equal to m upon I into y. So F is equal to this. So strain energy stored U is equal to, as we know, F square upon 2I into volume. This is per unit volume. If I multiply by the volume, I will get total strain energy stored. So strain energy stored for this elementary strip will be equal to F square upon 2I into volume. suppose for this strip, this cross section area is dA. So this is the area into length. This length is dx. This one is dx. See, multiplied by dx. So area into this is the volume. So this will give the strain energy stored for this elementary cylinder. So if I sum up all the elementary stuff from here to here for this portion from top to bottom, means sigma. So it will be sigma f square upon 2e into this one. So it means it will be f square upon 2e into sigma dA upon into dx volume. And if I put the value of f here, it will be this f is equal to 1 upon 2e, f is equal to f square means m square upon I square into y square. M square upon y square into y square. So this is the value of this into this one. So I will get this f square upon 2a into volume. This is the strain energy stored, and f is equal to m upon I into y whole square upon 1 upon 2e into dA upon dx. So it will be m square upon I square into y square upon 1 upon 2e into dA into dx. So it will be m square upon 2e I square. M square upon 2e I square into dx into this dA into y square. So energy stored by this dx length of the beam for this length from top to UI, it will be sigma of all such kind of small cylindrical strip. So this will be sigma m square dx upon 2ei square into this one. So m square upon 2ei square I can take outside. So it will be summation of dA into y square. And what is this? dA into y square. So area into y square. This area of his dA into distance from the neutral axis is y. So area into y square, the area into y square, sigma of this, what I will get? So I will get, this is the nothing but the moment of inertia. This is a moment of inertia I. So it means it will be I. So m square dx upon 2ei. M square dx upon 2i. So total energy of the whole beam is from x is equal to 0 to x is equal to L. If I integrate it, so it means total energy stored for the whole beam will be the integration of this m square dx upon 2ei. So this is the another way to derive this formula. So m square dx upon 2i is the, in case of bending it is this, and in a case of axial deformation it is a p square L upon 2ae. So similarly strain energy due to shear force is equal to q square dx upon 2n into as, where this q is the shear force on an element of length dx. So on a length of dx, my shear force is so it is like this. So this length is dx. So here shear force is q. So q into ds upon 2, n is modulus of rigidity. Modulus of rigidity, or I can say shear modulus, and this is the area of the cross-sectional area which depends on the shape of the cross-sections. So similarly, in case of shear, we can calculate the total strain energy stored. In case of torsion, as we know, similar to the axial force case, it can be shown that for torque acting on a circular bar of diameter d and length L, the internal strain energy stored is equal to T square L upon 2 Nj. So similarly, where J is equal to polar moment of inertia, which is pi d by 4 upon 32. D is the diameter of the bar, N is the shear modulus, T is the torque, and L is the length. So in case of torsion, we can calculate total strain energy is equal to this one. Deflection of beam from strain energy considerations. So deflection of beam from strain energy consideration, how we can do? When a beam is subjected to a point load or a couple, suppose this is a P. So if I want to know the deflection here, then I will say strain energy stored is equal to work done. Work done will be P into delta by 2. This is the work done, and this should be equal to the strain energy stored. Strain energy stored is equal to this m square dx upon 2I integration. So if I integrate from 0 to L, this is the formula for integrations, and work done is equal to 1 by 2 P upon delta. When I equate both, I will get delta. This is vertical deflection under the load. So this is the way for finding the deflections when a beam is subjected to a point load or couple. So in case of couple, so this rotation theta I can calculate from this. So in this case, work done will be 1 by 2 into m theta is equal to m square dx upon 2I. So I can find my theta, angle of rotation. So due to point load or due to rotations, I can find the slope or deflection by equating the work done is equal to total strain energy stored. When a beam is subject to a point load or a couple, the deflection under the load rotation due to couple can be found by equating the total work done to the total strain energy stored, but we cannot find the deflection or rotation at any point other than the point where load or couple is acting. For this, we can use either fictitious load method or Castigliano method or unit load method. What does it mean? Suppose if I want to know the deflection here, say delta. So for this, I cannot find this delta from this strain energy consideration. By equating the work done and strain energy, only what I can find the deflection under the load or rotation under the couple moment. So if I want to know the rotation here, suppose here this theta, I cannot find from this way, or delta. So at any other point I cannot find from this consideration. For this, I have to apply the fictitious method or unit load method or Castigliano theorem, which will be explained in the coming. Today, later on, I will explain the Castigliano theorem, and unit load method will be discussed in the coming lectures. Suppose this is my portal frame. A portal frame ABCD has its end, one end is hinged, other is placed on the roller. A horizontal force P is applied on the end D as shown in figure. Determine the horizontal moment of D. Assume all members have the same flexural rigidity. This is the horizontal frame. One end is hinged and this is placed on the roller. And there is a horizontal force of P which is acting at D. So obviously reaction of same amount of P will be here. If I want to know the horizontal deflections, well, this is delta H. Delta H is horizontal deflection, deformation. So under the load I can find. For this, my total work done is equal to total work done is equal to total strain energy stored. The work done will be, this is the load, and so this is a load into deflection divided by 2. This is the work done, and integration is equal to integration of m square ds upon 2ai, and this will be equal to the, for the whole frame, for this portion, for DC portion, it will be, my moment will be P into y. P into, at this point the moment is P into y. P into y, this is m whole square into ds. ds will be dy upon 2ai. If I integrate it from x, is this y is equal to 0 and y is equal to, this is h, this distance is h. So 0 to h, I will get strain energy stored for this portion. Similarly, for this portion also, this is, suppose this is Py, so it will be Py into whole square into dy upon di. I integrate from 0 to h. So both are same. So I will multiply this by 2. So this will be the strain energy stored for this portion and this portion. Plus for this portion, suppose if I take moment at x, the moment here will be equal to, as the horizontal load is acting, these are collinear forces, it means horizontal reaction will be 0, both are passing on the same plane, so no horizontal reaction will be there. So moment at this point will be this load into this distance, this is ph, this m square into this is dx, this will become dx upon 2i. I will integrate from x is equal to 0. If I say x is equal to 0 to b, this is b. So this way I will get total strain energy stored, and this will be, this is 2 upon 2ei means 1 upon ei. This p square I can take outside, it will be y square dy 0 to h plus this will be 1 upon 2ai into p square into h square into dx and 0 to b. So I will get p square upon ei, this will be y3 upon 3 means h3 upon 3 plus p square h square upon 2i into x, x is equal to b. If I take common p square h square upon 6ei, I will get 2h plus 3b. P square h square upon 6i into 2h, and this is my total strain energy stored. So total strain energy stored is equal to this one. So total strain energy is equal to the total work done. Total work done is equal to load into deflection P into delta H by 2. This is total work done. This should be equal to the total strain energy stored, which is P square H square upon 6 EI upon into 2H plus 3B. So delta H is equal to PH square upon 3 EI into 2H plus 3B. So this is the deflection delta H due to this horizontal force P, and this deflection is equal to P H square upon 3I into 2H plus 3B. So by equating the total work done is equal to total strain energy stored, we have found the value of the delta H is equal to this one, P H square upon 3I into 2H plus 3B. Now, work done by a force on a member. So far, what we have discussed, the work done is equal to load into deflection by 2. Load into deflection by 2. Suppose this is a simply supported beam and a horizontal vertical force W is acting at this C point, and there is a deflection of delta. There is a deflection of delta. The work done in this case will be 1 by 2 into this del W into delta. So this is the work done by this force. Now suppose if this force is not acting, there is a simply supported beam and a load of K is acting at this point K, and this K is very small load. This K is a very small load. So obviously deflection because of this very small load obviously will be very small. So this is the case. This Q is acting very small load. So work done because of this K will be 1 by 2 K into this deflection, and this deflection is, suppose this is delta delta. As we know, this deflection is very small and this load is also very small. So small is equal to into means very small. So I can say this work done I will neglect it. I will not consider it. In this case, if suppose I applied a load W, if I applied a load W, then my beam will further occupy this position. If I applied a load W here, then my beam will deflect in this way. Suppose because of this W which is acting at this point, there is a further deflection of Y under this load which is acting earlier than this W. So there will be further deflection of Y. So work done in this case will be K into Y. Why K is into Y? This is just a case of sudden loading. If I plot a load deflection diagram, then my load is already acting. This is not gradually. This is like this. At a 0 time, when the deflection is 0, this deflection, my load is acting. So this K is constant here. This K is constant here. and my deflection is varying. So the work done will be equal to the area of this triangle. This will be K into delta. Since the K is already acting, and because of this K, its work done due to this K, this is very small, so I have not considered this. It means work done in this case will be K into Y. What does it mean? It means work done because of the load under its line of actions will be equal to 1 by 2 W into Y, and this deflection is because of some other external force. This Y is not because of this Q. This Y deflection is because of this W. So in this case the work done is K. So what we have concluded? We have concluded that the work done by the load is K into Y. So if a load is acting on a member and produce a deflected deflection delta in the line of action by virtue of its own direct action, then the work done by the load is equal to 1 by 2 into W into delta. In this case, so because of its own effect, this W, work done in this case is 1 by 2 W into delta. But work done because of this, since this deflection is not because of this K, it is because of this W. So work done under this load, work done here will be K into Y. So if this deflection is because of some other external agency, then the work done will be K into Y. If the work done because of its own effect, this will be 1 by 2 K into delta. Since both are very small quantities, so this I have neglected. So this work done because of this deflection which has been caused by the external force, it is K into Y. Because of this W, if W is acting, I want to know the work done here, it will be 1 by 2 W into delta. So if a load acts on a member and produces a deflection delta in its line of action by virtue of its own direct actions, then the work done by the load is 1 by 2 W into delta. If a member is subjected to load K, is given a deflection Y in the line of action of K by virtue of some other external agency, then the work done will be simply K into Y. Now, law of reciprocal deflection or Maxwell reciprocal theorem. This Maxwell reciprocal theorem. So what this Maxwell reciprocal theorem states? What it states? Suppose this is a simply supported beam and the load W is acting here. Obviously it will deflect like this, and suppose there are 2 points, this C and this one is D. So because of this W, there will be some deflection under its load and there will be some deflection under this load also, under this load also. So due to this load, suppose this deflection is delta D here, delta D here. So deflection because of this load, deflection at D because of this load which is acting at C, this deflection because of this load is equal to deflection under this point by the load acting on D. So if I reciprocate them, then deflection at delta C will be same. Suppose this deflection is delta C because of this load acting at D. If I place this load W at D, then this delta C, because of this load, this delta C is equal to, so deflection at D, C, at C because of the load is at D is equal to deflection at D due to load at C. So this delta D, the deflection at D due to load at C is equal to deflection at C due to load at D. This is Maxwell Reciprocal Theorem. Maxwell Reciprocal Theorem. Suppose this is the case, I have applied a load W here. So suppose the deflection is, this deflection is delta C, this is delta D. Now if I further applied this load W at D here, so my beam will deflect like this, and because of this W at D, there will be further deflections, and this deflection will be, suppose this is delta C, delta D. So deflection at D, it will be delta D, and this deflection under this will be delta C. So total work done in this case, total work done in this case will be how much? This will be, first of all, work done due to this delta C will be 1 by 2 W delta C. Since this deflection has been caused by the load which is acting its line of action, so by virtue of its own effect W, the work done is 1 by 2 W into delta C. And work done because of this delta C small, this deflection has been caused by not this load, it has been caused by the load at another point D. So this deflection is because of some other externalities. So in this case, the work done will be W into delta C. So total work done will be this plus this, and work done because of this load, this W. So work done because of this W, this is the shape. Since this delta D is because of its own effect of load W which is acting at D, so work done because of this will be, due to its own effect, it will be W into delta D. So this is the total work done in this case. Now let's see if I reverse the order. This is my beam, my load is at D, W, and because of this load, the deflection small delta C, delta D. What happen if I place a load W at C? Then my beam will further deflect. So because of this W at C, my deflection will be, further deflection will be this. So due to this load, the deflection delta C and delta D, delta C and delta D. This will be delta C and delta D. Now let's total work done will be how much? So this delta C has been caused by its own effect of this W. So work done because of this will be 1 by 2 W into delta C. Now work done because of this load initially the work done due to this load is due to its own effect. So it will be 1 by 2 W into this delta D plus this deflection of delta D has been caused by not this load, this has been caused by this load, some other external agency. So not caused by this load. So work done because of this here, it will be W into delta D. So it will be W into delta D. So in both the cases, the total work done must be equal to each other. So this is a case number 1, this is case number 2. So they both are same, just I have reversed the order. So work done, this work done must be equal to this one. So it means this is equal to this one, 1 by 2 W delta C plus 1 by 2 W delta D plus W delta D. Now this and this will cancel. This one and this will also cancel. So it will be W delta C is equal to W delta D. So what I will get? Delta C is equal to delta D. And what is delta C? This is delta C is equal to delta D. This delta C is the deflection at C because of this load W at D. This delta C is the deflection at C due to the load acting at D, and this is equal to deflection at D because of the load at C. So this delta D is the deflection at D due to load at C is equal to deflection at C because of the load at D. So this is law of reciprocal theorem, or we can say Maxwell reciprocal theorem. What it says, that if this is a simply supported beam, I have 2 points. If I applied a load here, then there will be some deflection at this point. So this deflection at D because of this load must be equal to deflection at this because of this load at D. This is a Maxwell reciprocal theorem. So deflection at C due to load at D is equal to deflection at C due to load at C. This is what Maxwell reciprocal theorem says. If any beam or truss, the deflection at any point D due to load at W at any other point C, this is equal to the deflection at C due to the same load W at D. So this all which I have explained you. So this delta C is equal to, so this is Maxwell reciprocal theorem. Similarly, if suppose this is the beam and there is a couple mu acting at C. So rotation at D because of this couple at C, if I draw, this is simply supported beam, then this rotation at D due to couple at C, if this is a theta D due to couple at C. So because of this couple, my beam will deflect like this. This is C point, my couple at C. So there will be some rotation, and this rotation delta DC due to couple at C is equal to rotation at C due to couple at D. If I apply reverse D, if I applied couple in place of C, it is D here, then it will deflect like this. So rotation at C due to couple at D, theta rotation at C due to couple at D is equal to rotation at D due to couple at C. So this is second version of the Maxwell reciprocal theorem. And the another is, suppose this is the deflection beam and I have applied a load. So it will be like this. So this point is C, this is D. So, if I draw a tangent, then there will be a rotation. So, rotation at C due to load at D, rotation at C due to this load at D is equal to the deflection at D due to couple at C. So, slope at C due to load at D, slope at C due to couple at D is equal to deflection at D due to couple at C. So, both this deflection at D due to couple at C is equal to slope at C due to load at D. So, this is the third version of the Maxwell reciprocal theorem. Now, Betti's law. What is Betti's laws? What it says? In any structure, the material of which is elastic and follows Hooke laws, and in which the supports are unyielding and the temperature is constant, the virtual work done by a system of forces P1, P2 during the distortion caused by a system of forces Q1, Q2, Q3 is equal to the virtual work done by a system of forces Q1, Q2 during the distortion caused by a system of forces P1, P2. So, any elastic material which is elastic and follows the Hooke laws and there is no yielding, temperature is constant. So, work done, virtual work done by system of forces P1, P2 during the distortion caused by the another system of Q1, Q2 is equal to the virtual work done by system of forces Q1, Q2 during the distortion caused by system of forces P1, P2, P3. What is this? I will explain it this way. Suppose this is the case number 1, and if a system of forces P1, P2, P2 are acting. So, at this point, due to this load, suppose the deformation is Y1, Y2 and Y3. So, the deformation at this point is Y1, Y2 and Y3, and this is because of this system of forces P1, P2 and P3. There is the another case when another system of forces Q1, Q2 is Q3 and acting. So, deformation under this point, suppose this is small y1, small y2 and y3. This another system of loading is there. So, work done in this case, suppose I say W E dash. In the first case, work done is this. Suppose in the first case, this is the case, and applied this loading, then it will be further deflected. So, deflection further will be small y1, y2 and y3. So, total work done in this case will be work done of this plus this, and because of this small y1, y2 and y3. So, this will be, as this deflection has been caused not because of this load, it has been caused by this Q which is acting at this. So, work done because of this will be P1 y1 plus P2 y2 plus P3 y3. So, work done total will be this plus this plus this. Suppose this is the case. This is P1, P2 and P3. This is the one system of loading, and another system of loading is now deflection because of this P1, P2 and P3. Suppose at this point and this point is Y1, Y2 and Y3, and there is another system of loading which is acting at this point. This is W1, W2 and W3, or you can say this is Q1, Q2 and Q3. So at this point, because of this, the deflection is Y1. So at this point, this deflection is Y2. So at this point, is Y3. Now in the first case, acting here, if I apply the first case, I applied this loading at this point. So I applied this loading W1, W2 and W3. So this is the first case, and after this deflected positions, I applied this loading. So my beam will further deflect, and deflection at these points will be small y1, y2 and y3. So total work done will be, suppose in this case, in this usual loading, the work done is WE and this is WE dash. So work done because of this will be this plus this additional deformation at these points P1, P2 and P3. So this deflection has been caused not because of this P1, this is because of external other agency, W acting at other points. So if the deflection is not because of this due to other force, then work done will be P1 Y1 plus P2 Y2 plus P3 Y3. What will be the total work done in this case? It will be WE, this work done plus this one. So this will be the total work done. WE in the first case work done, this is WE dash and this additional work done. Now suppose this is the case. And deformation at these points is Y1, Y2 and Y3. So this one is the case. In the other case, this one. Now what happened? If work done is WE dash, obviously this one, and this is the another case. P1, P2 and P3. So at this position, this deflection because of this is Y1, Y2 and Y3, and work done is equal to WE. So now in the first case, in this deflected positions, if I apply this loading, then it will be this one. If in this deflective position I apply this loading further, so my beam will deflect further. I apply this load P1, P2 and P3 here. So at this point, deflection because of this P1 is equal to obviously this Y1 so total work done because of this will be this deflection Y1 Y2 has been caused by the force at other external point. This work done is not because of this Q1 Q2. So the work done will be, this will be Q1 into Y1, since it is because of this external force. So Q1 Y1 plus Q2 Y2 plus Q3 Y3. It means total work done in this case is WE dash, WE and this one. So this is the work done in this case. What does it mean? In the first case, my work done is this one, WE. In the first case, work done is WE plus WE dash plus P1 Y1 plus P2 Y2 plus P3 Y3. So this is the work done in the first case. So this work done must be equal to this work done. Since the net loading is same in both the cases, so this must be equal to this one, and this is WE dash plus WE plus this one. So this and this will cancel, this will all and this will also cancel, but I will get P1 Y1 plus P2 Y2 plus P3 Y3 is equal to Q1 Y1 plus Q2 Y2 plus Q3 Y3. So what is this? This is the work done by force P1, P2, P3 due to the deflection Y1, Y2, 3, Y3. This deflection is not because of this P1, P2, P3. This deflection is because of some another system of forces Q1, Q2, Q3 is equal to work done by Q1, Q2, Q3 due to the deflection this Y1, Y2, Y3, not because of this load, but because of some other external system of forces. So this Q1, Y1, Q2, it means this work done is equal to this one. So this work done Q1, Q2, Q3 is this load. and this deflection capital Y1, Y2, Y3 is the deflection not because of this load, this is because of another system of forces P1, P2 and P3. So, work done by this system of forces Q1, Q2 and Q3 due to the distortion or deflection caused by P1, P2 and P3. This Y1, Y2 and Y3 has been caused not because of this system forces Q1, Q2, this is because of this P1, P2, 3. This work done because we must be equal to the work done due to P1, P2, P3, and this deflection small y1, y2, y3 is not because of this, this is by due to another system of forces Q1, Q2 and Q3, these deflections. So, work done due to P1, P2, P3, so this is P1, Y1, this deflection is by because of this system of forces. So, P1 small y1, y2, y3 is equal to this one. So, this is the virtual work done by a system of forces P1, P2, P3 during the distortion caused by a system of forces Q1, Q2, Q3 is equal to the work done by a system of forces Q1, Q2, Q3 due to the distortion caused by another system of forces is the Betti's law. So, this total work done in this case is what I have explained. So, this work done due to this system of forces Q1, Q2, Q3 is because of this deflection Y2, Y3 and Y3 which has been caused by this load P1. So, this capital Y1, Y3 is the deflection due to this force. So, P1 into this Q1 into Y1, Q2 into Y2 is the work done due to the distortion caused by this P1. Work done by this Q1, Q2, Q3 due to the distortion caused by another system of forces is equal to the work done by this system of forces P1, P2 due to the deflection caused by Q1, Q2 and Q3. So, this is the Maxwell, this is Betti's laws. So, virtual work done by a system of forces P1, P2, P3 during the distortion caused by system forces Q1, Q2, Q3 is equal to the virtual done by system forces Q1, Q2, Q3 during the distortion caused by a system of forces P1, P2, P3. So, this all explanation I have explained. The first theorem of Castigliano. So, first theorem of Castigliano. This is a very important theorem. So, you must listen carefully. First theorem of Castigliano. What does this theorem says? In any beam or truss subjected to any load system, the deflection at any point is given by the partial derivative of the total strain energy stored with respect to the force acting at the point in the direction in which the deflection is desired. Means, suppose this is a system of load P1, P2 and P3, and if I want to know the deflection here, this YR, deflection at this point which is under this load P1 is equal to the partial derivative of the total strain energy stored with respect to this force P1 which is acting in the direction in which the deflection is desired. So, this deflection YR is equal to the partial derivative of the total strain energy stored by these forces with respect to this force PR which is acting at this point. Suppose I have a beam and there is a UDL, then a point load, and there is a couple also. and there may be some torque as well. So this is beam and different kind of loading is there. And I want to know the deflection at this point. Y1. So first I will calculate the total strain energy stored by this beam by this formula. So this will give the total strain energy stored. M will be this is the mx. So total strain energy stored, this is the formula. And after calculating the total strain energy stored, if I find the partial differential coefficient of this, partial derivative of this with respect to this force W1. Why W1? Because deflection under this load is this which I have to determine. So this deflection Y1 is equal to the total strain energy stored partial derivative of this with respect to this force. This will give the deflection here. Now, if I want to know the rotation at this point, suppose rotation at this point, so theta rotation at this point will be the partial derivative of the total strain energy stored with respect to this force. So partial differential coefficient of this total strain energy with respect to this couple will give the rotations. It may deflect like this. So the rotation at this point will be the partial differential coefficient of total strain energy stored with respect to this couple. And this is the torque. If I want to know the angle of twist means theta 1 means phi, you can say. This will the total partial derivative of the total strain energy with respect to this torque T will give the angle of twist. Or you can say, if a shear force is there, partial differential coefficient of the total strain energy stored with respect to the shear force will give the shear strain. So this is what Castigliano theorem is there. So its derivation I will explain here. So in any beam or truss subjected to any load system, the deflection at any point is given by the partial derivative of the total strain energy stored with respect to a force P1 acting in the direction in which the deflection is desired. So this is the beam. So its deflected shape is like this. Now if I remove all the loading, suppose, and a small load PR, this is delta PR, small incremental load delta PR, which is very small, I applied at this point R. I have removed all the loading and applied this. So my deflection shape will be like this. So the deflection will also be very small, delta YR. If in this case I applied this loading P1, P2 and P3 here. So because of this, my beam will deflect further like this, and this deflection is YR. This YR I have to determine. This deflection is very small. So work done, this work done because of this load in this first case will be 1/2 delta PR into delta YR. Since both are very small, infinitely small quantities, the product of this will be very small. So I can neglect this. So total work done in this case will be, suppose the initially the work done is WE. This must be equal to strain energy stored WI. So this is the first case. So in the second case, work done will be this one, first work done plus work done due to this deflection. This deflection YR has been caused by another system of forces, not because of this delta R. So this work done because of this will be YR into this load delta PR. So this deflection is because of another forces. The work done will be delta PR into YR, this one. So this is the work done in this case. So delta PR delta R. And this work done, suppose work done in the first case is this one delta, this is Wi, and there may be some change in the work done delta Wi due to this additional force. So this is the work done plus change in the work done delta Wi is the increment in this. So I will get work done in this case, and this will be Wi plus YR into delta PR. This and this will cancel. So this YR is equal to deflection at R is equal to delta Wi upon delta PR. This is basically internal work done, means strain energy stored. This is delta U also you can say. So the above relation is justified when this W delta PR, this incremental load, delta PR is infinitely very small quantity. So for this what I will do, I will put limit, and delta PR is approaches to 0 into this delta Wi into delta PR. So this will become YR is equal to partial differential coefficient of this one. This Wi is the internal strain energy. So I can also write U, delta U upon delta PR. So partial differential coefficient of the internal work done or strain energy with respect to the force PR. This force is this one PR. So partial differential coefficient of the total strain energy stored with respect to this force P will give the direction delta this YR. This is partial differential coefficient of the total strain energy stored with respect to force. This will give the deflection at IR. It means if I want to know this deflection under this load, so this is Y2. So this Y2 will be equal to partial differential coefficient of the internal work done or strain energy with respect to this force P2. This will give this deflections. Similarly, there is a moment M, and it may deflect in this way. So rotation at this point theta is equal to partial differential coefficient of the total strain energy stored with respect to this M will give the rotation theta at this point. The partial differential coefficient of strain energy stored with respect to this M will give the rotation. So this is Castigliano Theorem 1. So this is the first theorem of Castigliano, which is a very important theorem. So rotation theta at any point in the direction of the applied moment will be given by the partial derivative of the total strain energy stored with respect to the moment mr. Therefore, a generalized statement is as follow. If there is any elastic system in equilibrium under the action of a set of forces W1, W2, W3, Wn, and the corresponding displacement delta 1, delta 2, delta 3, delta n, and a set of moments m1, m2, m3, and the corresponding rotation is phi 1, phi 2, phi 3, and phi n, then the partial derivative of the total strain energy stored U with respect to any of the forces or moment taken individually would yield its corresponding displacement in its direction of action. Suppose there is a rotation here and there may be some torque. So this is a beam. So this one is a delta 1, this is delta 2, delta 3. So partial differential coefficient, and suppose because of this the rotation is phi 1, and suppose here is another couple, then some rotation is phi 2, then so there are some load and rotation is there. So partial differential coefficient of the total strain energy stored with respect to, suppose this is m1, will give the rotation phi 1. If this, then it will be delta u upon delta m2 will give the rotation here. Delta u upon delta m3 will give the rotation at this point. Similarly, deflection, this delta 1 will be partial differential coefficient of strain energy stored with respect to this force. This delta 2 will be given by the partial differential coefficient of the total strain energy stored with respect to this force. Similarly, delta 3, partial differential coefficient of the total strain energy stored with respect to this W3. So this will the deflection here. This is what Castigliano theorem is there. So this is a very important theorem and its application will be very large, and you will find number of questions based on this theorem. Second theorem of the Castigliano will be explained later on. So if it is required to find the deflection at any point where the force is acting, then an imaginary load, suppose this will give the deflection under the load. Suppose there is a beam and this is the loading P1, P2 and P3, and I want to know deflection at this point where no load is acting. This Castigliano theorem can give the deflection only under the load, this y1, y2, 3. If I want to know the deflection at this point, or you can say deflection at this point, what I will do? For this, I will apply a imaginary force. Suppose imaginary force Q. So there is an imaginary force Q. I will apply it, and I will find the total strain energy stored. Then partial differential coefficient of this strain energy stored with respect to this imaginary force delta Q will give the deflection at this point. So, and in the derivation, in the expression, finally after finding the strain energy stored and its derivative, I will put the value of Q is equal to 0. Since this Q is imaginary load, so I will put the value of Q is equal to 0 in the expression later on. That will give the deflection at these points. This is called imaginary load, or you can say fictitious load. So this way I can find the deflection at other point also where no load is acting. I will apply imaginary load, I will calculate the strain energy stored, then partial derivative of this with respect to the imaginary force will give the deflection at this by putting Q is equal to 0. So let's start the things by solving some numericals. The band ABC as shown in the figure carries a concentrated vertical load P at A. Find the vertical and horizontal deflection at A. Assume uniform flexural rigidity. So this is a frame. So I have to find the vertical deflection at this point and also horizontal deflection at this point. So vertical deflection, for finding the vertical deflection at A, I will apply the Castigliano first theorem. This deflection will be given by the partial derivative of the total strain energy stored with respect to this force P, which is acting in the direction of the in which the deflection is desired. Delta U upon delta P will be the deflection. So first I will find this U. U is strain energy stored U, and this will be equal to the m square dx upon 2I is the formula for strain energy stored. So I will integrate it first for this portion, then plus this portion, and summation of this portion plus this portion will give the this. So suppose if I consider for this portion, suppose this is x from here, so mx at this point will be p into x, this is m square, I put the formula px square into dx upon 2I. I will integrate x is equal to 0 to x is equal to a. So integration of this will give the strain energy stored for this horizontal part plus for this vertical part. Suppose for this there is a distance of y, the moment at this point will be this p into this distance which is a. It means at all the points my bending moment will be, because of this force P, will be constant, and this will be P into A. So moment is PA square into dx will be dy upon 2I. Integration from y is equal to 0 to y is equal to h. That will give the total strain energy stored. It will be P square by 2 EI into this will be x3 upon 3. So A3 upon 3, I will get this one. Then plus it will be P square A square upon 2I into integration of dy 0 to h, and this y will be y means P square A square upon 2I into h, and this will be P square upon 2I and integration of x square dx, then P square upon 2I, this will be x3 upon 3 means A3 upon 3. So I will get this one. So this will be P square A square upon 6I into A plus 3h. Now vertical deflection at A, this is YA, this vertical deflection YA here, this will be partial differential coefficient of the strain energy stored U with respect to P, means this is U. So partial derivative of this with respect to P will be this one, partial derivative of this one, and this will be, this will becomes 2P into 1 into rest of this A square upon A plus 3h into. So this will give the deflection YA. Now this will be P A square upon 3I into A plus 3h. So this will give the vertical deflection at A. Vertical deflection at A. Now for finding the horizontal deflections, since no load is acting in the horizontal direction, what I will do? I will apply a imaginary force, imaginary load Q in the direction of the horizontal direction where horizontal deflection is desired. Then suppose I applied this Q, this load is already acting. So in this case U will be integration of m square upon dx upon 2I is a formula. So U will be, for this portion it will be P into A, P into x. Here dx upon 2I, I will integrate from x is equal to 0 to x is equal to A. So Px, this Q will not create any moment in this horizontal portion. For this portion, this the formula. Then for this vertical portion at a distance of y, my moment will be this P into this. This distance will constant. This will be P into A plus, since the nature of both will be clockwise, so P into A plus Q into Y. Here into dy upon 2EI, and I will integrate it from y is equal to 0 to y is equal to h. So this will give the, total strain energy is stored, and horizontal deflection at Q. Suppose this is HA. This is the horizontal deflection HA will be equal to the partial derivative of the strain energy stored with respect to this Q will give the horizontal deflections. So partial derivative of this portion will obviously be 0, since no component of Q is there, so it will be 0, plus for this portion it will be 0 into H, it will be 2 into PA plus QI raised to the power 1 into coefficient of Q. So it will be since it is m square ds upon 2I, so it will be U. So delta U upon delta Q will be 2m, and then delta m upon delta Q into ds upon 2I. So it will be m into delta m upon delta Q into ds. So it means it will be 2 into PA plus QI into 1, and the coefficient of this will be y, and this is 2EI into y. So this and this we cancel. So it will be 1 upon EI into 0 to H, and after finding the partial derivative of this, I will put the value of Q is equal to 0. Since this Q is imaginary load, so I will put Q is equal to 0 here. So it will be P into A into Y dy. This PA I can take outside, so PA upon EI, and this YV will be y square by 2, means PA upon 2EI, and this will be y is h. So it will be PA h square upon 2EI will be the horizontal deflection at Q. So this is the horizontal deflection at Q. So another numerical, a beam of uniform section, and there is a beam of uniform section and of length 2L. This is my simply supported beam of uniform section and length is 2L, is freely supported by a ridged support at its ends, right end is freely supported, and by an elastic prop at the center. So this is an elastic prop, means some yielding is there at the center, some elastic prop is there. If the prop deflects by an amount delta times the load it carries, means there is a yielding, there is a deflection. So deflection, this deflection here at this point will be equal to delta times of the load it carries. So this, if this force is P, then deflection will be delta times of this. So this will the deflection under this load. So if the beam carries a total distributed load of W, so this is uniform distributed load and total amount is W. So its intensity will be W upon total length 2L. So this is the case. This total load is W, means its intensity will becomes, this is 2L. So this intensity will be W upon 2L. This will be the intensity, and it will deflect like this. And I have applied an elastic prop here. So this prop will try to deflect in the another way like this, but the net effect will be such that there will be some residual, there will be, so this is the final shape. So there will be some deflection at this point. So this deflection, downward deflection minus this upward deflection due to prop, this minus this will be this amount. This will be the net amount of deflections at this P. So this YB, YC, suppose this is the this is B, you can say this is C point. So this deflection, small deflection, this one is equal to delta times of the force it carries P, and this will be, and this deflection will be equal to the partial derivative of the total strain energy stored with respect to this prop P will give the deflection, this delta, this is YC, and this YC is equal to delta times of this prop, and obviously this YC will be negative. Why negative? Because the direction of the prop is upward and this deflection is downward. So my net deflection is, this deflection is downward from this baseline YC, and direction of the prop is upward. So partial derivative of the strain energy stored will give YC, means minus of the YC, since direction of YC and P is opposite. So net deflection is not in this direction, it is in the downward direction. So this will give minus YC, and this is equal to delta P. So first of all, I have to calculate the total strain energy stored, then I will find the partial derivative of this, and this I will put minus delta C, means minus delta P. With this I will get reaction prop, and this must be equal to this one. So this I have to prove it. So this is the case. A, B and C. This is the UDL. So total load is W. So I have applied a prop here. Obviously it will deflect like this. So after I applied a prop here, the effect of the prop will be something like this. So because of this loading and this prop, there is a net yielding is here. So this will become like this. There will be some deflection here, YC. So this is my prop P. So reaction here will be total load is W minus this P, that will be W minus P. This will be the total downward load remaining. This will be shared equally by both the reactions. So W minus P is the total load after considering its effect, W minus P, and that will be shared equally, W minus P by 2 and W by P minus 2. Now, if I consider a small x distance, so strain energy stored is equal to m square dx upon 2I integration. So for this portion, it will be W minus P by 2 into x minus the intensity is W upon 2L. This distance is x, so it will be W upon 2L into x square by 2. This will be the moment at this square of this and dx upon 2I. If I integrate it from x is equal to 0 to x is equal to L, this is L, this is also L. If I integrate it from 0 to L, I will give strain energy stored for this first half, and due to symmetry, first half is equal to second half, so I will multiply it by 2. This way I will get the strain energy stored. Now, delta U upon delta this prop will give the deflection at this point, YC. YC is equal to this partial derivative of this, and this will be 2 upon 2EI, I can take outside. So, partial derivative of this will be 2 into W minus P by 2 into x minus W upon 2L x square by 2 into 1, and then coefficient of this P, this will be minus x by 2 into dx. So, this will be this 2 and 2 I can take, this will be minus x W by P by 2 into minus x and this x, it will be minus x square minus x square, 1 upon 2I is here, into dx, and integration from and this will be minus minus plus W upon 2L into 2 into x cube. So, this into dx, and this will be 1 upon EI into integration is from 0 to L, it will be minus W minus P by 2 into, it will be x cube upon 3 into dx plus W upon 4L into x cube upon dx 0 to L. This will be 1 upon EI, this is minus W minus P upon 3 into 2 is 6 and this will be L3 plus W upon 4L into X4 upon 4 means L4 upon 4. So I will get this, and then this W minus pi minus upon 2EI finally into L cube upon 3 plus W upon 4 EIL into L4 upon 4. The calculation part you people can do, minus W minus PL cube upon 3 into 2 6I plus WL cube upon 16EI. Then it will be minus WL cube upon 6EI, and this minus and minus plus PL cube upon 6EI plus WL cube upon 16EI. Then it will be LCM of this will be 18EI. WL cube I can take common, 18EI. This will be minus 8 plus 3 plus PL cube upon 6EI, and this will be, and this will be equal to the deflection at C, and deflection at C is equal to delta times of proprietions, and the direction is opposite, so it will be minus delta P as I explained. So minus delta P is this YC is equal to minus delta P lambda P, lambda times of propriection, and direction of P and YC is different opposite, so this is why this is minus. So minus delta P is equal to this one. So now phi WL cube upon 18EI I can take it on the left hand side, then PL cube upon 6I plus this P into lambda. P I can take common, BL cube upon 6EI upon this. So P will be equal to phi WL cube upon 18EI into 6EI upon this one, the value of the P. Then if I take common phi upon 48 EI W L3 into 6 EI, if I take common L cube here, so it will be 1 plus 6 EI lambda upon L cube. This EI and EI will cancel, this will be 8, so it will be 5 upon 8 W divided by 1 upon 6 EI lambda upon L cube, and this is P. The value of the P is this one, and this I have to prove. In the question, the propriation is this one, 5W upon 8 into 1 plus 6 EI lambda upon L cube. So this is the formula. Obtained an expression for the vertical displacement of point A in the bent cantilever shown in figure. So this is a bent cantilever, it is like this, and I have to find the vertical displacement of point A, vertical deflection of the point A. So vertical deflection of point A, this vertical deflection of point A I have to find. So this YA will be equal to the partial derivative of the total strain energy stored with respect to this force W. This way I can calculate YA. So first I have to find the total strain energy stored. And what is total strain energy stored? U is equal to integration of m square into dx upon 2I and summation of all this. for different members. So with this I will calculate the strain energy stored. So let us draw its free body diagram for various parts. So for this portion it will be like this. This is W and this distance is A. So obviously this will be W, and this moment it will create a moment of W into A in these directions. So its resistance it will be W into A is this one. Then for this vertical member it will be, since it is upward it will be downward W, and this moment will be in the opposite direction. So it will in this direction, it will act in these directions. So this will be W into A. Similarly, here also it will be W, and to resist this there will be a moment of WA, and for this horizontal part this it will be downward, so it will be upward, and the moment will be like this WA, and here also at this point D my total moment will be, this is 2.5 A. So this W will create a moment of 2.5 WA in this direction. Oh, this is downward, this is upward. Oh, upward, this is downward, so this is upward. This will be downward. So this will be downward W. So this will be in opposite nature. So it will be W. So 2.5 WA will be this way, and this moment is WA. So it means total moment will be 2.5 WA minus WA. So it will be 1.5 WA. Balance will be this way. So for counteracting, this fixed end will provide a moment of 1.5 WA here. So this is the free body diagram of this portion. Where is member? So the first free body diagram for various member. Now there is a thickness of T, and this distance is 2.5 A at the center, 2.5 A from here to here. From the center of this is it is 2A, and from center of it is A. So moment of inertia of this portion, CD portion, if I consider first of all AB portion, let's consider AB portion first. So I moment of inertia will be, suppose on the plane of the paper the thickness is this one 1, and this is T. So moment bending moment will be along this one. So moment of inertia will be 1 into T cube upon 12, means T cube upon 12 is the moment of inertia, and at any distance x, mx will be, this will be hogging, so minus W into x, and since U is equal to the deflection at A will be the partial derivative of strain energy stored with respect to the force W, and this will be m square dx upon 2I, and this will be, first I will differentiate with respect to m, so it will be 2m and then delta m upon delta W into ds upon 2I, and it will be m into delta m upon delta W into 1 upon EI. So m at this point my bending moment is minus W by 2. So delta m x upon delta W with respect to this, it will be minus x. So this is for AB portion. For BC portion, for this BC portion, moment of inertia will be, this is 2t and moment will act in this, so it will be 1 into 2t q by 12. So this will give the moment of inertia. So it will be 1 into 8 t cube upon 12, and this will be 2 by 3 t cube. This is the moment of inertia. M here, suppose this is the distance, so m is equal to this one. So moment at this distance, this will be constant. This W will not create any moment, so it will be, if I consider this direction like that, and I will see here, so it will be hogging. So WA is the moment, and its coefficient with respect to W, since I have to find this delta m upon delta W force, so it will be A. This is for portion BC, and for portion this CD, for portion CD, moment of inertia will be, this is T, so it will be 1 into T cube upon 12. So T cube upon 12 is the moment of inertia. M will be how much? Suppose for this at a distance of x from here, so M will be, this will create a hogging moment, so it will be minus W into x, minus Wx plus this Wa. So it will be minus W x minus A, minus W into x, this will be hogging and this is sagging. It will be minus W x into A, and delta M upon delta W will be minus x minus A. Now YA will be delta U upon delta W, and this will be summation of integration of M upon delta W into ds upon EI, and this will be integration of this portion mx is minus wx into minus x into dx upon EI. This is for AB portion, so I will integrate from x is equal to 0 to A, plus integration for this portion BC portion, M is equal to WA, and delta M upon delta W is equal to A into dy upon EI, this is y, and y is equal to 0 to 2A. For this portion, it will be, this is for CD portion, so M is equal to minus W into x minus a into minus x minus a. So this minus and minus will plus into dx upon 2ei dx upon ei, and x will be from 0 to 2.5a. So this will, I will get delta u upon delta rho is deflections. So this is the bending moment diagram. So this is delta m upon delta I into corresponding I, and I will be different in all the cases. So in the first case, this I is E, I can take 1 upon E common, and I will be, in the first case it will be t cube upon 12, and then in this case t is equal to 2t cube upon this 1 upon E I can take, so it will be 2t cube upon 3, and in this case I is equal to t cube upon 12, so it will be E will be here and t cube upon 12. I mean, I will get this one. So after putting the value in all the cases, I will get this will be my equation. So E I can take common since E is constant and I will be different. So when I integrate it, so it will be 12w into x square into dx, 1 upon t cube I can take outside, so it will be 12w into x cube upon 3 means a cube upon 3 plus 3w a square upon 2 t cube I have taken already common, so it will be x means 2a plus 12w upon t cube is here, so it will be a minus x here whole square will be a square plus x square minus 2a dx, then 1 upon e t cube, this will be 4w a cube plus 3w a cube plus 12w into integration of this will be a square into this x plus x cube upon 3, x is 2.5a minus 2a x square by 2 means x this square by 2, this will be e2 cube plus 4 plus 3 is equal to 7 wa cube plus this will be 30 wa cube plus this multiplied by this will be 62.5 wa cube minus this will be 12 into this, I will get 75. So this will be 62.5 plus 30, 92.5 plus 9, it will be 99.5, 99.5 minus 75, hmm. $75, 62.5 plus 37, it will be, I think some, yes, 99.5 minus 75, it will be 0.5 or 4 and 2, so 24.5 wa cube upon e2 cube. So this will be the deflection, this will be the deflection at A. So its bending moment diagram will be like this. If I want to draw the bending moment, then suppose I am moving internally. I am seeing this beam here, I am seeing this and this, I am sitting here. For this portion, this will be hogging, means 1.5A, and here it is sagging, so it is WA. So it will be like this, it is hogging, this is sagging, this is for this portion. For this portion, if I am watching from here, then this is sagging and this one is also sagging. So its effect will be this and it will be WA. For this portion, if I see from here, then it will be in this way. It will be like this and the amount is WA, and if I am watching it from here, then this will be sagging. So either way you can draw the free bending moment diagram, either if I am moving internally or outside. If I see from here, then it will be different. So this is my bending moment diagram. This is the BMD. And the displacement deflection is this one. Find the vertical and horizontal deflection for the lamp post loaded as shown in figure. This is my lamp post and this is a 1/4 of a circle. So it is a 1/4 of a circle. This is an arc, and I have to find the vertical deflection and horizontal deflection of this. So it is a circular arc. So vertical deflection will be partial derivative of the total strain stored with respect to this P, and horizontal deflection at this point, since no horizontal load is acting, I will apply a imaginary force Q, then it will be delta Q upon delta partial derivative of the total strain energy with respect to this Q. So after finding the differentiating and putting Q is equal to 0, I will get the horizontal deflection. Let us see how I will proceed. So vertical deflection is equal to strain energy stored is equal to m square dx upon 2I. So for this portion, suppose so if I consider here small, this is dx and this is radius, suppose this theta is d theta. So this dx will be r into d theta. In the formula, m square dx upon 2I, my this dx, if I expressed in, then this will be dx is equal to r d theta upon 2I, and m square will be m bending moment at this will be, this is the load and its horizontal distance will be this one. This is r and horizontal projection will be r cos theta, r sin theta. This is r sin theta. So m will be p into r sin theta. It means it will be PR sin theta. This is the moment PR sin theta. So m square into dx, which is r d theta upon 2i. If I integrate it from theta is equal to 0 here and theta is equal to 90 degree here. So if I integrate from 0 to pi by 4 2, I will get strain energy stored for this portion plus for this portion vertical frame. Suppose this is y. So moment here it will be, this distance is constant, so it will be p into this one, and this is r radius. So p into r m square into dx. So it will be dy here, not dx, into integration from y is equal to 0 to h. I will get this strain energy stored. So u is equal to, this is, I will get so this will be p square r cube upon two ei, and this will be sin square theta d theta integration from 0 to pi by 2 plus this will become PR square p square r square upon 2 ei, and this will be dy. So this where I will get p square r cube upon 2 ei, and integration of sin square theta 0 to pi by 2 is equal to pi by 4, and this one is p square r cube into y, and y will be h upon 2 ei. So this will be p square r square upon 8 ei, I can take common. So inside it will be p square p square. So this will be p square r square upon 8 ei. So it will be pi r plus 4 h. This is u, and the partial derivative of this delta u upon this force p will give the vertical deflection ya, and this will be 2 p r square upon 8 ei into pi r plus h. This will be, and this will be p r square upon 4 ei into pi r plus h. So this is the equation for vertical deflection. Is 2p, this is p r square upon 4 ei into pi r plus h, and this is p r square upon 4 ei pi r plus h. This will be 8, then it will be 4h. So this is for vertical deflection. For finding the horizontal deflections, what I will do? I will apply a horizontal force here. For finding the horizontal deflection, I will apply a imaginary force Q here. So now U will be delta U upon delta Q will give the horizontal deflection. So let's find the Q is a, U will be for this portion, it will be P R sin theta because of this, and this Q at this point, this distance will be the perpendicular distance, and this will be R cos theta. This is R minus this R cos theta will give this one. This will be R into 1 minus cos theta, and effect will be same. It will be PR sin theta plus Q into R into 1 minus cos theta. This will be the moment. This square into dx will be R d theta upon 2 EI, and integration of this from theta is equal to 0 to pi by 2, this point, plus for this portion it will be P into R, and this will be Q, effect of this will be Q into this will be R plus this Y. So total this distance will be R plus Y. This square into dy upon 2 EI integration from 0 to y is equal to 0 to h. Now as we know, delta u upon delta q will be, this will become partial derivative deflection, horizontal deflection will be partial derivative of this with respect to q. It will be 0 into pi by 2, it's 2 EI R in upon 2 EI, I can take common, so it will be 2 PR sin theta plus QR 1 minus cos theta raised to the power 1 into coefficient of this is, coefficient of Q is R, coefficient of Q is R into 1 minus cos theta coefficient, and this is d theta. So this will be delta, this will be m into delta m upon delta q into ds upon ei. So this will be this one, and for this portion it will be 1 upon 2 ei into 0 to h, and this will be PR plus Q 2 into PR plus Q into 2 plus y into 1, and coefficient of this will be R plus y into dy upon 2a. And after finding its derivative, I will put the q is equal to 0. By putting q is equal to 0, this will eliminate, this will also eliminate. What I will get? I will get this one, horizontal deflection HA, this will be equal to this and this, it will be R upon EI integration of 0 to pi by 2, this will be PR sin theta into this R I have taken common into 1 minus cos theta into d theta, plus for this portion it will be 0 to h, and this will be PR plus this portion will eliminate, it will be PR into R plus y into dy, and this PR I can take common, PR so if I take this common, so it will be P R square upon EI into sin theta 0 to pi by 2 into d theta minus 0 to pi by 2 into sin theta cos theta into d theta, plus it will be PR into integration of this will be R plus y square by 2 means h square by 2. So this way we can calculate it by putting q is equal to 0. I will get finally this one, and this will be integration of sin theta is equal to minus cos theta, so I will get plus 1, and this will be sin 2 theta by 2 means minus 1 by 2, and sin theta means minus cos theta, so minus cos theta means so divided by 2, and I am putting the value, then it will be minus cos theta, so minus cos pi by 2 minus cos 0, so it will be minus minus plus, and this is minus, so I will get this one plus PR upon EI RH plus h square by 2, this will be PR cube upon 2I, finally I will get this one, and then so finally I will get this one PR upon 2I in this is h square plus y square r square plus 2s, so PR upon 2I is equal to r plus h square. So this is the final horizontal deflection at A. Find the vertical deflection of the joint D for the truss loaded as shown in figure. All the members have the same sectional area. So this is the truss, and I have to find the vertical deflection at this point. So for finding the vertical deflection at this point, first formula is vertical deflection at point D, YD means partial derivative of the total strain energy stored with respect to this force P, this equal the vertical deflections, and strain energy stored will be how much? As in case of axial member, it is S square L upon 2E. So in case of axial member, X square L upon 2E is the formula. So summation of this of all the members, S square means the force in any member square of this into length upon 2A, and summation of all this I will get total strain energy stored. Then I will find the derivative of this. So this will be equal to the vertical deflections. Let's find the force. This angle is 45 degree. It's 45 degree. This is 45 degree. This is 90. This is 90. So this is also 90, 45 degree. Suppose I want to know the force in this member. So this will be, this angle is 45 degree. Let us resolve the forces along this direction. If I resolve the forces along these directions, so it will be P into sin 45 degree. P into sin 45 degree means it will be P upon root 2. So P upon root 2, its component will be this way. So force in this member will be opposite to this, means it will be P upon root 2. This is the force in this member. Now if I resolve the force along this direction, then component of this force will not be there, it's 90 degree. Only component of this will be there. So it will be P cos 45 degree. P cos 45 degree means P up into this. This will act in this direction. So effect of this should be opposite to this. Force in this member will be P upon root 2. So this is the force in the member. Now what happens? Suppose if I resolve the forces along this line at this point, then component of this force will not be there since it is 90 degree. Only component of this force will have to nullify the effect of this force. So component of this force, this is obviously 40 degree. So this will be, suppose this is x, so it will be x into sin 4, it will be x into cos 45 degree. This is x and sin 45 degree, x cos 45 degree. This force must act in this opposite direction. So it will be x cos 45 degree should be equal to this force. And this is x into 1 upon root 2 is equal to P upon root 2. It means x is equal to P and direction is same. So this force is P. It means this force is P. Similarly, if I will resolve the force at this point along this direction, this is 90 degree. So component of this force will not be there. Only component of this will be, this will be P into cos 45. This is 45 degree. So this will be cos 45 in this direction. Component of this will be. So force in this member obviously should be act in this way. And this is P cos 45 degree must be equal to the force in this member. And this should be upward. So this is P upon root 2. It means force in this member is P upon root 2. So this is the force in this member. Now if I resolve the force at this joint along this line, this angle is 90 degree. So force in this member will not have any component in this direction perpendicular to this. So this must be equal opposite to this, and the same force will be there. Let's say P upon root 2. Similarly, at this point, if I resolve the forces vertically, then component of this will not be there. So this is 45 degree. So component of this will be P root 2 into 45 degree, cos 45 degree means this one, and this force in this member, well, this is x, so it will be sin 45 degree. It means this x is equal to P upon root 2. So this force will be, since this is downward, so component of this should be upward. So this will be like this. And if I resolve the forces along this line, then same force but of opposite direction will be there. Since component of this force will not have any effect if I resolve the forces along this line. Now at this joint, component of this will be like this. It will be P upon root 2. This is 45 degree. So P upon root 2 into cos 45 degree. The direction will be this way. And the component of this is 45 degree will also have a same effect. So this will be P upon root 2 into cos 45 degree. So it will be P upon root 2 into 1 upon root 2. This P upon root 2 into 1 upon root 2. This will be P by 2 plus P by 2 is equal to P. And both the forces are acting in this direction. It means force in this direction will be this way, and this will be P. So this force is P. Now, if I resolve the forces along this direction, then component of this force will not have no effect. This is 90 degree. So only component of this will, this is 45 degree. So this will be P cos 45 degree means P by root 2. So this force will act in this direction. So force in this member should be opposite to this. It will be P upon root 2. This P upon root 2, and similarly this is P upon root 2. If I resolve the forces vertically, then component of this will be P upon root 2. This is 45 degree, this one is also 45 degree. So P upon root 2 into cos 45 degree plus this will also act in the same direction. So P upon root 2 into cos 45 degree. It will be P upon root 2 into 1 upon root 2 plus P upon root 2 plus 1 upon into 1 upon root 2. So it will be P by 2 plus P by 2 means P, and both will act downward. So component of this will be and this also force in this member will be cos 1 upon root 2. So 1 upon root 2, 1 upon root 2 will be cancelled. So it will be 2 P upon root 2. So it will be root 2 P. So root 2 P is the force. Root 2 P So this force will obviously have a component on the vertical upward, so it will be root 2p. Similarly, at this point, if I resolve the forces along this direction, then component of this force will not be there. So only effect of this will be there. So it will be 45 degree. So P into cos 45 degree means P upon root 2. This will be upward. So force in this will be downward, and P upon root 2. This will be the force. This is P upon root 2. Now, if I resolve the forces, this one, if I resolve the forces vertically, then suppose this force is x. So x into 45 degrees, so it will be x. Cos 45 degree means x upon this. This should be equal to component of this will not have any effect. So component of this will be there. It will be P upon root 2 into cos 45 degree will act downward, plus because of this also it will be P upon root 2 into 1 upon root 2. So this will cancel and it will be 2p upon root 2 means root 2p. So force in this will be root 2p. So this is the force. And this will be upward. Now, so if I resolve it, then its component will be this is root 2p into cos 45 degree means, so this will be p means there is a horizontal direction of p here, and if I resolve it vertically, then it will be same. So it will be p upward. Similarly, at this point, if I resolve it, so it will be p in this direction, so it will be p, and this component in the horizontal direction down, so there will be upward directions of p. So now I have calculated the forces in all the members. So total strain energy stored is equal to S square L upon 2 AE. Means U is equal to, and I have this is P upon root 2 P upon root 2, P upon root 2. In how many members the same force P upon root 2 is there? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So in n member, force is P upon root 2. So 8 times of this force square into its length. Length is L. This length is L upon 2AE. So I will get 8 into S square L upon 2AE. So 8 members I have this one, this one, this one, this one. So 1, 2, 3, 4, 5, 6, 7, 8. I have calculated. So remaining is in this it is P. This also P. So in 2 member force is P. So P square into length. This length will be how much? This length will be, since this is L, this is 90 degree, this is L, this is L, L. So it will be L root 2. So L square plus L square root, it will be L into root 2. So L into root 2 is the length of this member. The same is with this. So length is root 2L upon 2AE plus, so this and this I have done. Now remaining is this and this. 2 member force is root 2P. So this square into length. This length is obviously equal to L upon 2AE. So this way I have get the total strain energy stored. So it will be P square L upon 2AE. If I take it common, then inside it will be 8 P square L upon 2AE. I take common, so it will be 8 divided by this is 2 plus P square L upon 2AE. It will be 2 into root 2 plus this P square L upon 2AE I take common. So this will be two. The square of this will be 2. So this is 4 and 4. So it will be P square L upon 2AE. This will be 4 plus 4, 8 plus 2 root 2. If I take common, if I take 2 common, so I will get the U is equal to P square L upon 2AE. If I take 2 common here, it will be 4 plus root 2. This and this will cancel. I will cancel. This will be P square L 4 plus root 2 upon AE, and partial derivative of this U with respect to this force P will give the deflection at this point D, YD, and this will be partial derivative of this will be 2 P L into 4 plus root 2 upon AE. So this is the vertical deflection at this point, 2 PL upon AE into this one. So this total strain energy stored is a summation of this the force in all the members, this is 2 PL upon AE into 4 plus root 2. So 2 PL upon AE, 4 plus root 2, this is the final vertical deflection. So this is a question which came in Engineering Services 2001. So using Betti's theorem, determine the elongation of a bar of 10 mm diameter and 1 meter long when it is subjected to a force of 10 kilonewton at diametrically oppositely at midspan of its length. Take E is equal to this one. So E is equal to 2 into 10 raised to the power 5 megapascal means Newton per mm square. Poisson ratio is equal to 0.3. So using Betti's theorem, I have to find the Betti's means Maxwell reciprocal theorem, both are same. So what does it mean? I have to find the elongation in these directions. So the force is acting at the midpoint and it is diametrically oppositely like this, 10 kilonewton and 10 kilonewton. At this point my cross section will be like this. So elongation because of this in this direction is equal to elongation in this direction due to force at B. So what does it mean? This is 10 kilonewton, 10 kilonewton. So obviously because these are acting diametrically oppositely, so elongation will be something like this. And this elongation in this direction, suppose this is delta, will be equal to, when I applied the same force of 10 kilonewton here, then whatever elongation it will produce in this direction here, suppose this is delta 1, or I can say this is longitudinal direction, so I can say this is delta D. So Maxwell reciprocal theorem or Betti theorems, what it says that my elongation in this direction because of this force at this point which is acting diametric opposite here. So elongation because of this is in this direction is equal to elongation in this direction because of the force if I applied at this point when the elongation is desired. So whatever elongation when I applied the same force at this point, it will create a in the lateral direction elongation. So elongation because of this in this direction is equal to elongation in this direction due to the same force applied at this. This is what Betti's theorem says. So it means if I have to find the elongation, this elongation because of this force, which should be equal to the elongation in this direction because of this. So this delta L here will be equal to this delta D. So for finding this delta D, I will find this delta D, and this delta D will be how? Because of this will be, this is a compressive force. So load, this is in kilonewton, divided by its area. Area of cross section is how much? So its diameter is 10 mm is the diameter. So pi by 4 into 10 square I will get the area. So what is the formula for elongation? This is PL upon AE. I will get this elongation in these directions. This the elongation in this direction will be in the longitudinal directions. Because of this compressed force, there will be PL upon this one. PL upon AE. So P is this one, area is this, length is 1 meter, I think. So this will be 1000 mm divided by E. E is equal to this. So this will be the elongation in this directions. But I have to find this delta D, which is equal to this delta because of this. So this delta L, this elongation because of this diametric opposite force due to this must be equal to the elongation in this direction due to this force, and this must be equal to, and this delta D will be equal to this elongation into Poisson ratio, because this is lateral. So lateral upon longitudinal, lateral strain upon longitudinal strain is equal to Poisson ratio. So lateral strain is equal to mu into longitudinal strain, mu into longitudinal strain. So this is my change in length, this is my change in length in these directions. When I divide it by length, I will get strain, and this strain, longitudinal strain, when I multiply it by Poisson ratio, which is 0.3, I will get lateral strain, and this lateral strain is change in elongation divided by original length. So change in dia will be, when I multiplied it by this dia of 10 mm, I will get these elongations. So first I will find elongation in these directions, then elongation in directions. So it will be so this and this will cancel, and this is, that will be 10. So it will be so 2 into 0.3 upon pi into 10 square. It will be 2 into 3 by 10 is 1000 into pi is, it will be 21 upon 11 into 10 raised to power minus 3. So it will be 1.21 upon 11 is equal to 9. So it will be 1.9 into 10 raised to power minus 3 something mm. I will get this one. So it will be 1.91 into 10 raised to power minus 3 mm. So this is the end of the lecture. So I hope you enjoyed my lecture. Thank you very much and good night.